So recall in the last video we defined what a theorem calculation or gamma proof is, and essentially a theorem calculation is very similar to the formula calculation that we defined in our first class because it simply consists of a finite sequence of well-formed formulae following steps or rules. So the first step or rule is that we can write a formula from either lambda or gamma. That means that we can write any axiom or any of our assumptions at any step of a theorem calculation. And the second rule is that we can write the conclusion of an instance of an inference rule, or the denominator of an instance of an inference rule, provided that all of the formulae within the numerator of this same instance have been written at a previous step or in previous steps. So now that we know what a theorem calculation or gamma proof is, we can finally define what a theorem is formally within our logic. So any formula A that appears in a gamma proof is called a gamma theorem, and we denote this and read it as gamma proves A. So this symbol is called proofs. Notice that this is a statement in the meta theory because none of these symbols are within our logic. So essentially, whatever the well-formed formula A represents will be within our logic, and this will be a theorem within our logic, or a gamma theorem. But when you're asked to show gamma proves A, you're being asked outside of logic to show this with inside logic. So when you are asked to show gamma proves A, you're asked to write a theorem calculation or a proof of A, and such a proof or formula calculation is said to prove A from gamma, where we call gamma is the assumptions for this theorem. Recall that we may not have any assumptions, so gamma may be empty, in which case we simply write proves A, and you may be asked to show proves A, which means essentially to show that the well-formed formula represented by A is an absolute theorem or a logical theorem, and then you would simply use the axioms and rules of inference within your formula calculation. Some additional terminology. So a gamma proof is also called a Hilbert proof after the famous mathematician David Hilbert, who formalized theorem calculation to ensure that everything that is proved in mathematics is stable. So it comes from something rigorous that has no contradictions or paradoxes. Okay, so let's look at a particular example of a theorem calculation provided by Hilbert. So we are going to write Hilbert-style proofs following this particular framework. So when you're asked to prove gamma proves A, you're asked to write the theorem calculation for A in the following way. So we're going to number each sequence, each well-formed formula in our theorem calculation. So you'll write the number 1 and write either an axiom or an assumption from gamma, and the annotations are used to explain the step written in the proof. So because the first step of a theorem calculation says that we can only write a well-formed formula from lambda, or axioms, or a well-formed formula which is in gamma, or assumptions, then we would simply write one of those well-formed formula and identify either it as an axiom or as an assumption. Okay, and we would continue to write different axioms or assumptions until we had enough well-formed formula within a numerator of a rule of inference to be able to write a conclusion of a rule of inference. And we want to think ahead to what it is we're trying to prove and use the appropriate axioms and rules of inference to be able to conclude A at some point. Okay, so we stop as soon as we get to A because we are asked to prove A, and once A occurs in a theorem calculation, we have a gamma proof or a Hilbert proof of A. So in a Hilbert-styled proof, the conclusion appears at the last step. Although, by definition, it isn't wrong to have more unnecessary steps because, remember, A is a theorem as long as it appears in a gamma theorem. But as long as it appears, essentially, we just want to stop. All right, so in class, we'll actually apply this theory to really see what it looks like. I think at this point it's a bit difficult to see, so we'll look at some of these simple theorems and identify how to write Hilbert-style proofs for them.